Let's take a look at Chapter 30, Glass, Glazing, and Light Transmitting Plastics. Clear glass, as we know it today, came into commercial use at the end of the 17th century with the invention of the glass-making process by Bernard Perrault. In Perrault's process, molten ingredients of glass were first cast in a mold and later spread into sheets by rollers. When the glass solidified fully, it was ground and polished on both sides with abrasives. The mechanism of the rolling and grinding operations brought down the price of glass significantly so that it could be used commercially in mirrors and in storefronts. Although the process of manufacturing modern glass is substantially different from that of the cast or cylindrical glass of the several centuries ago, the ingredients are virtually the same. In this chapter, the modern process of manufacturing glass, as well as its various types and their properties, are described. Also discussed are light transmitting plastics, which are sometimes used in lieu of glass. This large glass pyramid emits light into an underground addition to the Louvre Museum in Paris, France. A transparent cube of glass supported by light steel structural backup encloses the Rose Center for Earth and Space in New York City. Let's take a look at the manufacture of flat glass. The primary raw material for making flat glass is sand. Chemically, sand is silicon dioxide, also called silica. Sand used for glass manufacturing is obtained from sandstone deposits. Although silica is all that is needed to make glass, other ingredients are added to modify several of its properties. The two major ingredients added to silica for making flat glass are sodium oxide and calcium oxide. That is why flat glass is sometimes referred to as soda-lime glass. Soda-lime glass consists of approximately 72% silica, 15% sodium, and 9% calcium oxide, and 4% of other minor ingredients. In the process that is commonly used today, the raw materials are granulated, mixed together, and loaded into a furnace, where they melt. The process is controlled so that the predetermined thickness of molten glass travels continuously over the tank of molten tin, called the float bath. At the end of the annealing layer, the glass sheet emerges as a continuous ribbon at room temperature, free of any internal stresses. It is then cut into desired lengths by automatic cutters, packed, and transported to its destination. The glass obtained from this process is called float glass, to distinguish it from sheet glass and plate glass, which were the two types of flat glass are used before the discovery of the float glass manufacturing process. Let's take a look at types of heat-modified glass. There are three types of heat-modified glass: tempered glass, heat-soaked tempered glass, and heat-strengthened glass. Flat glass obtained from float glass process without any further treatment is basic glass, referred to as annealed glass. Tempering is the exact opposite of annealing. Whereas annealing, the process of slow cooling after heating, reduces or eliminates locked-in stresses, tempering produces them. When heat-treated glass is quenched with cold air during the tempering process, the outside layers of the glass become hard, while the interior remains hot and soft. As the interior of the glass cools, it shrinks and tends to pull the hardened outside layers inward, producing compressive stresses in them. Because the outside layers have already hardened, they resist the inward pull. Consequently, the interior of the glass comes under tension. These stresses are permanently locked into a tempered glass sheet. Tempered glass is approximately 4 times stronger than annealed glass in bending. It can also withstand greater deflection than annealed glass of the same thickness and is far more resistant to impact and thermal stresses. When tempered glass breaks, it breaks into tiny square-edged cubicle-shaped granules, a breakage pattern usually referred to as dicing. Annealed glass, on the other hand, breaks into long, sharp-edged pieces. Tempered glass is therefore used in hazardous locations provided that it meets the requirements of safety glazing. The primary use of heat-strengthened glass is in situations where the glass is subjected to large thermal stresses. One such situation is the spandrel area of an all-glass curtain wall. This is a section through an all-glass curtain wall showing spandrel glass and vision glass areas. Although monolithic glass has been shown in the spandrel area, the same insulating glass unit used in the vision area may be used in the spandrel area. Why does tempered glass explode? Spontaneous breakage is less of a problem in heat-strengthened glass. When heat-strengthened glass breaks, most of it stays within the opening, similar to annealed glass. Tempered glass, on the other hand, fractures into small pieces and tends to evacuate the opening. There's generally less optical distortion in heat-strengthened glass. Let's take a look at glass and solar radiation. When solar radiation falls on a glass surface, part of it is transmitted through the glass, part is reflected, and part is absorbed by the glass. An 1/8 inch thick clear glass sheet transmits approximately 85%, reflects 10%, and absorbs nearly 5% of solar. A commonly used measure of how well a glass sheet performs with respect to direct solar radiation is the solar heat gain coefficient. The solar heat gain coefficient is equal to solar energy gained through a glass divided by solar energy incident on the glass. Another measure closely related to the solar heat gain coefficient is the shading coefficient. The shading coefficient is equal to the solar heat gain coefficient of glass in question divided by the solar heat gain coefficient of 1/8 of an inch clear glass. Because transparency is the primary reason for using glass in buildings, another important property of glass is its ability to transmit light. Visible transmittance is defined as the percentage of visible part of solar radiation transmitted through glass. The light to solar gain index of a glass is the ratio of visible transmittance and solar heat gain coefficient. Radiation in general has an adverse effect on human skin and eyes. It is also responsible for fading the colors of fabrics, carpets, and artwork. Manufacturers of glass quote the ultraviolet transmittance, UVT, of their products. A glass with lower UVT is generally preferable. Let's take a look at types of tinted and reflective glass. Two commonly used glass products that are specially produced to lower solar heat gain are tinted glass and reflective glass. A glass may be either tinted, reflective, or tinted and reflective. Tinted and reflective glass is commonly used in the curtain walls of an all-glass building to reduce unwanted heat gain through the building. The most commonly used colors in tinted glass are bronze, gray, and blue-green. If everything else is the same, a green tinted glass has a higher LSG index than any other tinted glass. Reflective glass works as a mirror from the outside during the day, hiding interior activity. At night, however, the interior activity is visible from the outside when the interior space is lit. A reflective coating on the outside surface of glass is more effective in reflecting solar radiation compared to with the coating on the inside surface. Several high-rise all-glass buildings located on opposite sides of a narrow street with reflective glass facades may make a street, particularly a narrow street, unduly warm in the summer due to multiple reflections of solar radiation. Let's take a look at glass and long-wave radiation. The properties of glass, solar heat gain coefficient, visible transmittance, and ultraviolet transmittance discussed previously are relevant only with respect to solar radiation. The properties of glass with respect to long-wave radiation are shown diagrammatically on this slide. Long-wave radiation absorbed by float glass from a warm interior and its dissipation by radiation and convection to a cold exterior. Observe that the majority of interior heat is dissipated to the outside. Very little returns to the interior. A simple way to reduce the heat loss of interior heat absorbed by glass to the exterior is to coat the surface of the glass with a low emissivity, a low E film. The glass with a low emissivity coating is called a low E glass. A low E coating is almost invisible to the eye because it transmits most of the visible solar radiation. With the use of low E glass, most of the energy is reflected back into the warm interior. Let's take a look at insulating glass units. A sealed assembly consisting of two glass sheets with an intervening space is called an insulating glass unit. The most common used IGUs in commercial construction is a 1-inch unit in which the total width of the unit, the thickness of the two glass sheets plus the width of the space, is 1 inch. Let's take a quick look at R value or U value of glass. Knowing that the R value of a single sheet of glass is approximately 1, the approximate R values or U values of other glass products can be obtained from Table 30.1. Manufacturer's data must be consulted for precise values. Using the information on Table 30.1, these are the approximate R values and U values of various types of IGUs. Note that the U value is the inverse of the R value. This is the end of Chapter 30, Sections 30.1 through 30.7. Chapter 30 quiz is now available.